We're now going to use a series of variational arguments, which may seem a little subtle, okay? But here is how they work. Okay. Now since that the previous equation holds, right? Since this equation holds for all W belonging to V, okay, right? Since it holds for all W belonging to V, it also holds for the following, right? Supposing we have a W which is minus divergence of P minus BF, okay, that vector sum, multiplied by some other function which I am going to write as C, depending upon x. Okay, so it also holds for this function if C function of x is a scalar function, right, which is greater than 0 in omega naught, okay, but goes smoothly to 0, right, on the boundary. Okay, then it definitely holds for that function as well. Okay, right, because you observe that by the fact that it goes to 0 on the boundary, we are making sure that W is indeed equal to 0 on partial of omega naught t. And you recall that we had no other requirement on W, right? So this particular choice of W also is a legitimate choice for W to be used in that integral equation we have on the previous slide. When we apply this, what do we get? We get integral over omega naught chi function of x divergence of P minus divergence of P minus BF dotted with itself dV plus for the second integral, the one on the traction boundary, we get chi x times minus divergence of P minus BF dotted with Pn minus T dA all equal to 0. But then remember this fact here, chi vanishes on the boundary, right? All right, chi vanishes and in fact we've chosen it to vanish just on the traction boundary, okay? But that implies that this entire term is equal to 0, okay? Leaving us with a situation where integral over omega naught chi function of x times the Euclidean norm of our vector divergence P plus BF the whole square dV equals 0. Okay? Now, since this is a Euclidean norm of a vector, it is greater than or equal to 0. By construction, however, we've chosen chi x to be greater than 0 on omega naught, right, on the inside of omega naught. It vanishes on the traction boundary, but on the inside of omega naught, it is greater than 0. Okay? However, the right-hand side says that this is equal to 0. So the only way this can work is if divergence of P plus BF equals 0 in omega naught. What we've done here is obtain through variational arguments the static balance of linear momentum. Okay? All right? Now, we can do things differently, right? Now reconsider the full integral form, right? Which is integral over omega naught minus divergence of P minus BF dotted with W dV plus integral over the traction boundary Pn minus T dotted with W dA, right? All of this equals 0. But we've just shown, just above here, we've shown that this term is equal to 0 in omega naught. Okay? So that implies that we always also have integral over omega over the traction boundary Pn minus T dot W dA equals 0. Okay? Right? Now again we can do something easy. We can say that, all right, let's choose well, let me not say choose. Let me say the following. This thing has to hold again for all W belong to V. Right? All W belonging to V. Okay? So that means it also holds for W equals, we can do the same sort of argument now, right? We can say that it also holds for maybe W equals chi1 of x times Pn minus T, where chi1 of x is greater than 0 on just the traction boundary, okay, right? And we don't really care what chi1 of x does on the other parts of the boundary, right? Because this integral involves only the traction boundary, okay? So again, this means that we have integral over the traction boundary chi1 of x times, just as we did before, right? When you use the fact that we've got this particular form for W, we're considering this particular form for W, we get okay, again, this term is greater than 0, this term is greater than or equal to 0, right? The only way this can work is if that integrand or the Euclidean norm is exactly equal to 0, right? Which means that Pn minus T has to be equal to 0 on partial omega naught T. Okay? So, through our variational arguments, let us look at what we have. So, the variational arguments have led us to the following, right? Okay. For all, actually we don't need to say that. What our variational arguments have led us to is this following set of equations. We know that divergence of P plus BF equals 0 in omega naught. We know that Pn minus T equals 0 on the traction boundary. Okay? And observe that this is just our traction boundary condition. Okay? Also observe that this boundary condition sort of emerges naturally from our variational arguments. Okay? And therefore, in the context of mathematics and the context of variational methods, this thing is also often called the natural boundary condition, BC for boundary condition. Okay? Now, all of this worked out for U belonging to S, right? Where S, remember, is all functions U such that U satisfies the displacement boundary condition. This condition is an essential condition for our variational arguments to have given us this set of equations, because it was the use of this condition, the one I've just drawn a brace bracket under, which also led us to require a homogeneous condition on our variation, a homogeneous boundary condition on our variations W on this part of the boundary. Okay? So this part, of course, we observe it is our displacement boundary condition. But because of the way in which it was required for our space S, it is also called an essential boundary condition. Okay? Now, our PDE here and these conditions, these boundary conditions, together constitute what is called the strong form of our problem. Okay, and this is called the strong form because really this is a form that is required to hold pointwise, right? It has to hold at every point in omega naught and every point on the boundary. Okay, so we say that this is the strong form of the balance of linear momentum for static problems. Okay? And remember that we've demonstrated through variational arguments that this strong form is obtained from the weak form. Okay? The two forms are actually completely equivalent. It's also possible to start out with the strong form in this manner, multiply it by a variational field W, do integration by parts, and go back to the weak form. Okay? So, let me just state that the variational arguments show that it is obtained from the other form that we started out with, right? This integral form. Okay? Now, this I referred to as the weak form previously. right? This is the weak form of the balance of linear momentum for static problems. Okay, it's called the weak form for a couple of reasons. You observe that it has, first of all, it's written in integral form, right? It does not hold pointwise. Okay. The other thing one can show is that so that's part of the reason why it's called the weak form, okay, because it holds in integral form. The other reason is that if you recall that P is equal to derivative of psi with respect to f, where f itself is equal to, f itself is obtained as a displacement gradient, okay, and then in the strong form we have another divergence of P. Okay, what this implies is that we have more derivatives being applied to our displacement field, because already P depends upon the gradient of u, and then we're going to take another divergence of P. Okay, all right, so this form means that there are more derivatives in the strong form, fewer in the weak form, right? Because P itself does not have a derivative on it. In a sense, that derivative on P has been shifted to W. Okay? It is in this sense that we also call this the weak form. It has fewer derivatives. Okay? Okay? However, the weak form and strong form are completely equivalent. What we've shown here is how we could get the strong form from the weak form. It's also possible to go from the start with the strong form and end up at the weak form. Okay, so let me just state that here. Weak form and strong form are equivalent. Okay, and it is the weak form that is the basis of many numerical methods, of so-called variationally based numerical methods, right? For instance, the finite element method. Right? The strong form, on the other hand, is the basis of methods such as finite difference methods. Okay? We'll stop here. So what we've observed is that variational methods are very powerful. The use of variational principles allows us to make statements about equilibrium conditions for nonlinear elasticity. We observe that when we do this, we get an integral form of the equilibrium condition, right? It's what I refer to as the weak form, and very importantly, that weak form is completely equivalent to the strong form, right, of the balance of linear momentum for static problems, okay, where we call it the strong form because of the pointwise application. We call it the weak form, on the other hand, when we have this integral form and the fact that there are fewer derivatives on the displacement field, okay, but they're completely equivalent. Okay, a question I'd like to leave you with is for you to think about why we didn't obtain the full dynamic balance of linear momentum through this equilibrium process. Okay? Think about that. All right, we'll stop here.